In this video, I will discuss the organic chemistry questions of JEE Advanced 2014 paper 1. The first question is about IUPAC nomenclature. Here we have to find out the correct combination of names for isomeric alcohols with molecular formula C4H10O. The first option is tertiary butanol and 2-methyl propane 2-ol. So this is tertiary butanol, the common name of this particular alcohol, and 2-methyl propane 2-ol. So propane, that means 1, 2, 3 carbon in a chain, and with the second carbon we will have the methyl group as well as the OH group. So 2-methyl propane 2-ol. So if we now check, we will see that tertiary butanol and this 2-methyl propane 2-ol are basically the same compound. So option A is one of the correct options. Now if we check option B, we have tertiary butanol. We already have the structure of tertiary butanol like this, and along with that we have 1,1-dimethyl ethane 1-ol. So 1,1-dimethyl ethane 1-ol. So if we want to draw the structure ethane, that means we have to keep 2 carbon and 1,1-dimethyl. So we have to keep the 2 methyl groups attached with the same carbon, and also 1-ol. So the OH group will also be there with the same carbon, with the number 1 carbon. But the problem is that this is not the correct way of nomenclature according to IUPAC rules, because in case of IUPAC rules we have to keep the longest chain. So longest chain means longest chain with carbon atoms, and we have to name the compound according to the longest chain. So in this case it cannot be a ethane. We have 3 carbon which will be the longest chain. So this 3 carbon will make the longest chain. That means we have to name it not ethane, it should be a propane. So the correct name for this compound will be 2-methyl propane 2-ol, but it is not happening here, so the option is wrong. So we have to go to option C, where we have N-butanol, that means normal long chain butanol. So 4 carbon in the same chain, there is no branching here, and OH at one end, that is normal butanol. And butane 1-ol is basically the same thing. So if you keep the 4 carbon in a chain like this, and with number 1 carbon, if you attach the OH group, it will be butane 1-ol. And if you check with this normal butane, it is basically the same compound written in opposite way. So this option is also a correct option. Now about isobutyl alcohol. So this is isobutyl alcohol. This is the common name of this specific alcohol, and 2-methyl propane 1-ol. So 2-methyl propane, that means the longest chain will have 3 carbon, 1, 2, 3, and with the second carbon we have the methyl group, and with the first carbon we have the OH group. Now if you compare this structure with this structure, you will see that both are basically same. So option D is also a correct option. So option A, C, D are correct for this specific question. In this question, there is a starting material which is a substituted phenol, and we are reacting this phenol with halogen, and we have to predict the product form after the reaction with the halogen, and also we have to find the reason behind the product formation. So it is already written here that if X2 is iodine, it will be a mono-halo substituted derivative, and of course the substitution will be in this region. That means ortho to the OH group and away from the bulky tertiary butyl group. So it is away from the tertiary butyl group because iodine itself is also little bit bulky, and the tertiary butyl group is very bulky. So iodine will not come near to these two ends. We know that phenolic OH always increases the electron density in this region, that means in the region of 2 ortho position and 1 para position. So the electron density here will be increased, and halogenation will always occur. I would say the chances of halogenation will be higher in these 3 positions. But in case of iodine, which is quite large in size, it will try not to come near this tertiary butyl group, which is also a bulky group. So these two chances, that means this ortho and these para, is prohibited. So here iodine will not come. So for iodine, the only option is the other ortho position, which is away from the tertiary butyl group. So the iodination will happen here, and a monohalo compound will be formed. In case of bromine, which is little bit smaller compared to that of iodine, so in this case dibromination will occur, but then also only one para and one ortho. Of course, there is only one para in this system, so we will have substituted bromine in the para position as well as one ortho position, not this one, because this one is between the OH and the bulky CCH3 group. So these two groups will cover the space in such a way that a bromine will not like to come near this place. So it will not come to this place, and a dibromo substituted compound will be formed, where the bromine will choose the second ortho position, which is away from the tertiary butyl group, and the para position. In case of chlorination, chlorination is much more smaller than chlorine is much more smaller than bromine or iodine, so trichloro product will form. So the chlorination will occur in both the ortho position and the para position too, and the bulkiness of this tertiary butyl group will not affect the chlorination. So what are the things that is affecting this product formation? First, the steric effect of the halogen, of course, because iodine is doing the reaction in different way, bromine is doing the reaction in different way, and chlorine is also doing the reaction in different way. So option E is correct, option A is correct, sorry. And the steric effect of the tertiary butyl group, yes, because the tertiary butyl group is bulky and it is not letting the bigger halogen to come near to it. That means the steric effect of the tertiary butyl group is also playing a role. The electronic effect of the phenolic group, of course, because that is the phenolic group which is directing the halogens to these two ortho position and the para position. So this is also a correct option. The electronic effect of the tertiary butyl group, no, there is no such effect from the tertiary butyl group. As we have seen, it has a steric effect, but it doesn't have any electronic effect which can decide the product formation. So option D is not correct. So we have A, B, C, the correct answers. In this question, a starting material which has two NH2 group will react in presence of acetic anhydride. So acetic anhydride is written here. The font is very small, so probably you cannot see it, but acetic anhydride is written in this position. So it will react with acetic anhydride in presence of DCM or dichloromethane, which is the solvent. So now we have to predict the product in this reaction. So what we have to do, first let us think about the reaction mechanism. So whenever there is an amine involved, it will react with the acetic anhydride in this manner. So the lone pair of nitrogen is going to react with one of the carbon in carbon, and then of course there will be a cleavage. So there will be the formation of CH3COOH, which is acetic acid, and a new amide will form. That means the first step of the reaction is the attack of the lone pair of nitrogen to the carbon in carbon of the acetic anhydride. Now let us take our compound, our starting material. This is our starting material. Now we have two amines here, two nitrogens with lone pairs. Now which one is going to react with this acetic anhydride? Obviously this one, which is already connected with a carbonyl carbon, will have lesser electron density over it, because the lone pair of the nitrogen is shared with the carbonyl carbon, the carbonyl oxygen. That means it will be less available, so it is not going to react with the acetic anhydride. But this one is not engaged in any other work, so it will react with the acetic anhydride, and the product will be this one with an acetic acid. as a byproduct. So if we check our options now, we can see that this one, option A, is the correct answer. In this question, we have to predict the total number of stable conformers with non-zero dipole moment for the following compound. Now, to understand that, we have to draw all the conformer, all the possible conformer. What we have to keep in mind? We have to keep in mind that the conformers must be stable and it must have a non-zero dipole moment. So let us draw the conformer. First, let us project this molecule in Newman projection, and if we just directly project the Fischer to the Newman, we will get this eclipse conformer, and of course this eclipse forms are not stable, so unstable. So this one is unstable. Then there is the second conformer. So I am just rotating this carbon, the nearest carbon, to 60 degree at a time. So if I just rotate it 60 degree, this new conformer will form, and here we can see that it is stable because it is a gauche conformer. So the atoms are not eclipsing on one another, so it is a gauche conformer, and of course it will be stable, and there will be a dipole moment. So mu is not equal to 0. In the next case, again, if we rotate this 60 degree, then these CH3s are going to eclipse one another, and along with the CH3, all the other atoms will eclipse one another. That means it is unstable. So we will not consider this one. Next, if we just rotate again 60 degree, we will get this conformer. Here we can see that it is a stable conformer because the atoms are not eclipsing one another, and there will be some dipole moment because these Cls, the dipole moment of these Cls are not cancelling each other. So it will have a dipole moment in this direction. So mu will not be equal to 0. Here again, if we rotate this 60 degree, then again we will get an eclipse conformer which will be unstable, so we will not consider this. Then again, if we rotate another 60 degree, this one, we will get a gauche conformer, that is the atoms will not be eclipsing one another, and of course there will be some dipole moment. As a result, we can say mu is not equal to 0 here, and it is also stable because it is not eclipsed. So 1, 2 and 3 conformer will be there, which will be stable without with non-zero dipole moment. In this question, we have to find out the total number of distinct naturally occurring amino acid obtained by complete acidic hydrolysis of the peptide shown below. So here is the peptide. What we have to do, we have to break the amide linkages to find out the amino acid with which these peptides are made of. So now if we break the amide linkages, I have already given the instructions here. That means the small red lines you can see are the amide linkages. So we have to break along this red line, and we have to add a proton to the nitrogen and a OH group to the ketone. Then we will get the amino acids from which these amides are made of. So let us start from the beginning. So if we take this one, we have one set here. This is amino acid, so this will be like this. So OH, so I am adding a OH with the carbonyl and an H2 here, and then again this part will give us something like this, NH2 COOH. So this is a glycine, and this one is also a glycine. So glycines are naturally occurring amino acid. So at least we have one naturally occurring amino acid. Next, let us take this one. So this whole thing is going to give us something like this. So I am going to add a OH with the carbonyl carbon and an H with the amine. So here we go. So this one is not a naturally occurring amino acid. So we can just leave this and let us take the next one. This is the next one. So again the same way, what we are going to do, we will add a OH group to the carbonyl carbon and a H to the nitrogen. So like this. So C double bond O and the OH here and NH2 here. This is also not a naturally occurring amino acid. Again there is the same thing coming here. So if I take this part, again I will get this compound. Sorry, not this compound but the other one. That means yes, this one again. Here also, if we just disconnect this part, again the same compound, this one. For the next breaking or cleavage, if we break this compound, of course we are going to get something like this. So from here we will get this compound. So here we will have the double bond OH and then CH2, a triangle here, then nitrogen, I will add a H here, then single bond CH2, OH here, along with that a glycine again, NH2, CH2, COH. So we can see here that the only naturally occurring amino acid that can be found is the glycine. So from this peptide we can get only one naturally occurring amino acid. All the other amino acids that are formed are not naturally occurring one. In our next question, we have to consider all possible isomeric ketones, including isomers of molecular weight 100. All these isomers are independently reacted with sodium borohydride. You have to note that stereoisomers are also reacted separately. The total number of ketones that give a racemic products are, so we have to find, first we have to find all the isomeric ketone with molecular weight 100, then we have to do a sodium borohydride reduction and we have to check that in which case a racemic product will form. So first of all, if we go for molecular weight 100, that means you need C6H12O, then only it will be 72 plus 12 plus 1600, and with these atoms you can construct a ketone like this. This is the simple ketone, so it will not be an aldehyde, a ketone. So the carbon will be in between, not at the end. So we have this simplest possible ketone with molecular weight 100, and we have to also take all the other isomers including the stereoisomers. So if we just try to draw all the other isomers, it will be, there will be 6 isomers. So 1, 2, 3, 4, 5 and 6. These 6 isomers are possible. Now among these 6 isomers, which one is going to give a racemic product on reaction with sodium borohydride? So Racemization is something where a optically active product will form and both the enantiomer will form in equal amount. In that case, a racemic mixture will form. So this is the basic of racemic product. That means both the enantiomer will form at same amount, so they will cancel out the optical rotation and there will be no rotation, and that is racemic product. Now we have to check that which among these 6 ketone are going to give optically active center and 2 enantiomers after reduction with sodium borohydride. So let me check one by one. So if we take the first ketone, we will get that one chiral center is formed, and of course this is going to give a racemic product. So this one is going to give a racemic product. So 1 I am writing here because there is only one chiral center which is formed due to this reaction. So this is going to give you a racemic product. That means plus and minus both the enantiomer is going to form. Fine. In the next case, in the starting material we don't have any chiral carbon, and after the reaction with sodium borohydride we are getting one chiral carbon. That means a racemic mixture will form with both the enantiomer in equal amount. In case of option 3, here also we don't have any chiral center in the starting material, but after the reduction we are getting one chiral center, and hence this will be a racemic mixture with both plus and minus enantiomer in same amount. Then comes the fourth one. Now in fourth one you can see that the starting material, the starting ketone itself has one chiral carbon. That means there could be 2 enantiomer possible, and in the question you can see that we have to take stereoisomers are also reacted separately. That means we have to take both the stereoisomers plus and minus, then we have to react with sodium borohydride. So suppose we are taking the plus isomer, so this is plus. Now what we are doing, we are reacting it with sodium borohydride, and of course a new chiral center is forming here with the old one here. That means we have now 2 chiral centers, and the new chiral center here could be either plus or minus. The probability is equal. So 2 different compound is going to form. One will have plus plus, that means the first chiral center which we have already taken as plus, so it will be plus, there will be no change of that chiral center. The new could be plus, and another possibility is that plus minus, that the new is minus in this case. So you can see that 2 different compounds will form, and these 2 compounds are not enantiomer of each other, rather they are diastereomer of each other. That means a racemization will not occur, because racemization is only possible when 2 enantiomers are formed in equal amount. Here we can see that 2 enantiomers are not formed, only 2 different diastereomers are formed. That means this option is cancelled out. So this number 4 ketone is not going to give you a racemic mixture. If we come to number 5, we can see that there is no chiral center in the beginning, but after the reaction a new chiral center is formed. Hence 2 different enantiomer will form in same amount. That means a plus minus mixture, racemization will occur. In this case also we don't have any chiral center in the beginning, but after the reaction with sodium borohydride we are getting a new chiral center. Hence again plus minus enantiomer in same amount, hence racemization. So 1, 2, 3, 4, 5. So 5 among the 6 ketone is going to give a racemic product after reaction with sodium borohydride. If you have liked my video, please click the thumbs up button as well as share the link with other people. And for more videos, please subscribe my channel and press the bell icon. Most importantly, please comment below about your needs related to chemistry so that I can make more videos on several other topics.